Hey, so there's going to be a quick video on Bayes' theorem as presented in an introduction to statistical learning, and I'm making this video because to me, the way that the authors define Bayes' theorem is not very intuitive. And what I aim to do with this video is for someone who doesn't have a lot of experience with Bayesian statistics, I'm going to try and make it clear why this thing is presented as it is. The reason I personally don't think that this is a clear definition of Bayes' theorem is because this is technically just the definition of a conditional probability. So this thing on the left is literally, by definition, equal to the probability that y equals lowercase k and x equals lowercase x divided by the probability that x equals lowercase x. We're going to try and get to this result, and you'll see that to get to this, you use Bayes' theorem, and that's the reason that the authors present this whole thing as Bayes' theorem, which again, I don't think it's intuitive. So anyway, to read this whole thing on the left, let's take a look at the definition. So y is a categorical variable, so this is going to be a classification problem, and y can take on multiple classes, so 1, 2, 3, 4, all the way up to uppercase k. Then x is a categorical variable. This is just, without loss of generality, they chose to use a categorical variable because with a continuous variable, you would need to use integrals, and that's really not a very intuitive way to teach someone about Bayes' theorem, all right? Then they define pi sub k as the unconditional probability that y belongs to class k, and they define f sub k of x as the conditional probability that x equals lowercase x given that y belongs to lowercase k. This is important because from a frequentist perspective, you typically try to estimate this thing directly, right? So think about what you do in logistic regression. You try to estimate the probability that y equals 1 given that x is equal to your vector of observable characteristics. And you do that with a sigmoid function, maximum likelihood, to try and estimate those parameters that approximate the probabilities that basically maximize the maximum likelihood function. And here, what we are going to be doing is we are going to find estimates for pi k and f sub k of x, and plugging these into this formula over here, and we will never have to directly estimate this thing on the left. That is the principal difference between what we normally do in logistic regression, for instance, and what we do with generative models of artificial intelligence. So the last definition, which isn't defined in the book, but this is just a definition, is the conditional probability of A given B. All right, so the conditional probability of A given B is equal to the probability of A and B divided by the probability of B. All right. And as you know, we are always allowed to multiply by 1. So if we multiply by the probability of A, divide by the probability of A, this equal sign still holds because we are only multiplying by 1, right? So if you take a closer look, you'll notice that this and this is equal to the probability of B given A, okay? And we have these two terms left over, so we're just going to put them in here. Probability of A divided by probability of B. All right, so this here, this equality is actually, this equation here is Bayes' theorem, okay? That is Bayes' theorem, and you use this thing to get to here. And we'll see this in this video. So let's take a look at what pi k, this numerator thing means, all right? So let's just derive what this thing actually means. So pi k sub k times f sub k of x is equal to the probability that y equals k multiplied by the probability that x equals lowercase x, given that y belongs to k, lowercase k. Using Bayes' theorem, or actually the law of conditional expectations, we can rewrite this as the probability of y equals k. Nothing's changed here. And here we can just say this is a probability of x equals lowercase x, intersection y belongs to lowercase k, divided by the probability of y equals k. And you'll see that these two terms cancel out. So just as a general definition here, we can just put this in a nice little box here so we don't forget. This is literally just equal to the probability of x and k. Okay? I'm just going to get a different color and just circle this thing here. So now we know that the numerator is equal to the probability of this intersection, and we only have to basically understand what this thing at the bottom here means. So let's just derive that super quick. We have that the sum of L equals 0 all the way up to uppercase K of pi k sub k, actually that's sub L, multiplied by f sub L of x is equal to, and I'm just going to, expand this super fast. It's pi of 0 f0 of x plus pi 1 f1 of x plus all the way up to uppercase k, right? Because we have k plus 1 classes, so there's going to be pi uppercase k f sub uppercase k of x, which, as we know from this thing over here, is equal to the sum of the intersections. Okay, so PR of x equals lowercase x intersection y equals 0 plus probability that x equals lowercase x intersection y belongs to class 1 plus a bunch of those, and we eventually get to the probability that x equals x intersection y equals uppercase k. So, as you should know from your very early lessons in probability theory, this is just the sum of the marginal distributions over all the values of k, of y. So it's y0, y1, y2, y3, y4, all the way up to y uppercase k. And as we know, this is literally just equal to the probability that x equals x. The unconditional probability. And this is, again, just a definition. We know that the unconditional probability that x equals lowercase x is equal to the sum of the conditional probabilities over all values of y. So combining these two results, we can see that this thing up here is equal to the intersection that y equals k and x equals x. And this thing at the bottom is equal to just the unconditional probability that x equals x. Okay, so that is how you use Bayes' theorem to get to this result. And I'll try to reiterate super quick why this is important. So again, in logistic regression, we would typically be interested in estimating the probability that, let's say, y equals 1, given that x equals x, as, the sigmoid function, which I think you use this thing. It's a phi. I'm not sure what symbol you use, but let's say use g, the sigmoid function of a bunch of parameters, beta 0, beta 1, all the way to beta uppercase K. All right? And so we're directly estimating this probability, this conditional probability. And here in Bayesian statistics, we can very easily observe pi sub k, because pi sub k is just the unconditional probability that y equals k, and we can see this or estimate this from our training data, because you just take the number of occurrences when y equaled lowercase k, divide by the total number of observations in your training data set. So this is super easy. And then, you typically make a few assumptions about how the joint distribution of all your features to try and estimate this thing, which is a little trickier to estimate. But the thing here is that once we have estimated pi sub k and f sub k for all k, we can basically get to this conditional probability without estimating it directly. And that is the most important thing about Bayesian statistics.